by taking this. Perhaps, let me check. Let's try maybe 18, or perhaps yeah, 18, maybe 18. Okay. So let's try number. Which one you prefer? From 17 to 21. Maybe 80 or 18. Okay. So 18 is basically we are given the set of a integration, double integrals, 4x plus 8y dx. And then we have the r. It says that it's parallelogram with this points as its vertices. And then we have these relations between x and uv, y and uv also, right? And it says that the instruction, although if the instruction is not given, we can always assume that they are having relations between these variables, right? So that means if we want to compute the 4x plus 8y, and perhaps there are two ways, at least which steps you need to take. First is perhaps the points for the r. Maybe you can pin the point and then look at the region of r, what kind of region that we are getting. Although it's not necessarily to draw, but if we want to draw, I think it's okay. Perhaps we could draw, and actually we don't need to draw, but we can perhaps observe what kind of region that we are getting. So we have -1 and 3, perhaps here. And we have 1 and 3. And then we have 3, let's say here it's 3, and then -1. And then 1 and 5. 1 and 5 may be around here. So, oh, wrong point. It's not here. So it should be 1 and -3. -3 is here. -3. -3, 1 and -3. So it should be there. And then 1, 5. 1, 5 is maybe around here. So we have that. Okay. If you want, you can also evaluate this R, find the linear equations, and then do the double integrations. I think just like regular solutions in double integral. So find the linear equation and then take into the double integral, and make sure that we are creating a separate area. I think we need to make it into two areas, area 1, area 2, right? But since we have this information that's given, so let's try this instead. Okay, instead of taking into this graph, we can use this relations between x, y, and uv. So since we have, so this is 18. So we have the x is 1 over 4 u plus v, and y is 1 over 4 v minus 3u. So what should we do first is perhaps, I think my suggestion is to get to know the Jacobian value. And how is it? So basically, Jacobian, we want transformation from xy to uv, right? So we want to transform xy to uv. So this is Jacobian that we want, okay? And then we are taking this, and then this will be partial x, partial u, partial x, partial v, partial y, partial u, partial y, partial v. And taking the partial x with respect to u, so this will be 1 over 4 and 1 over 4. And this will be partial y, partial u. U is negative 3, so negative 3 over 4. And then the last one will be 1 over 4. Okay. So take this determinants. So we are going to have 1 over 4, because both are 1 over 4, so 1 over 4 minus plus 3 over 4, so 1 over 4. Okay? Okay? Or you could just cross multiply, but I would like to factor out 1 over 4 because they have both 1 over 4. So this is our Jacobian value. So this is expected to be multiplied. Oh. And then, what is the question? The question is this 4x plus 8y. So let's exchange x and y through u and v that we have here. U and v is here, and v. Okay. So let's write again. The formulations is, let me write the questions. 4x plus 8y dA. Okay. All right, so we change the, let me write maybe 4x plus 8y. So 4x plus 8y become 4, 1 over 4, u plus v, and then plus 8, 1 over 4, v minus 3u. So we have, this will be u plus v, 2v minus 6u. So need to be plus, so 3v minus 5u. Okay, 3v minus 5u. And then, since we know also from our graph here that this will be a, this is r, right? R. And if you check the line equations with the slope you can take it from this triangle here, right? So at least you have 6 and 2, so it's around this will be 2, this will be 6. And we would like to get the slope. So 1 over 3, and then plug in all the point, or perhaps we can write the either this is just
reminder that we can do this. And since the m or the slope is negative, so I will write this as negative m, or since we know that this will be 1/3, so I will write this and change all with 1 point. Let's say 1 and -3. So this will be +3 and x -1. So y is one five. Okay. Oh wait. Why this negatives 1/3? Why? Should be 6/2. Sorry. It should be -3, right? Okay. Why I'm confusing. Okay, sorry. So -3x plus 3. Okay. So now it's correct, right? Am I doing correctly? Let's check the other one here. Let's check this one. So this will be 2 and 2. So either you check the check this one and this one. This should be similar slope, right? Or check this and this. Either way, you will have, I think, better approach. This is also, this will be slope is 1, so y minus 5 x minus 1. So y minus x is plus 5, so 4, right? Okay. So either you can check this and this, or this and this. Okay. I think I choose this one. I think because maybe it's simpler because it has 3. So I will take this. Okay, I will take this and then get another one. Y plus 1. And then x minus 3. So this will be y minus x is minus 4. Okay, so I will take this too. Okay. Yes?
Is y equal to minus 3x plus 3?
This one? Oh. Oh yeah.
I forgot to get rid of this. Should be 0, right?
Yeah.
Okay. Okay. So either using this or that. So we can say that the R, let me write here. R is bounded by this line. Okay, I will take the line that is y minus x equal 4 and y minus x equal -4. Okay. And then this y equal -3x, and this, if you want to know this one, then this will be y minus 5 -3 x minus 1. So minus 3x plus 8, right? Plus 8. And the -3x plus 8. Okay. Okay, and then from this part, so since x is 1 over 4 u plus v, y is 1 over 4 v minus 3u, we can build up x and y in terms of u and v. Okay, so we are going to solve in u and v. Okay, so this would be I will take in turns. This becomes u plus v for y. I will write u first and then plus v, and I will minus this 2. 4x minus 4y is 4u, or x minus y is 4. Okay, and then y is 4. Y is 4. Oh my god, what's happened to me? Okay, and then we can get this one here. I will take 12 3u plus 3uv 4y. I will add and canceling this 2. So 12x plus 4y is 4v. So 3x plus y is v. Okay. So let me mark this first so that I will not forget. Okay. So what will be this in terms of the graph? If we transform this xy into a perhaps, so let's draw the equations of the u and v. So we can try to plug in some of the points, like from the vertices. So let's say we try from 1, 5. So taking 1, 5. So 1 minus 5 will be minus 4. So u is minus 4. Let's say minus 4. And then v, this is u, this is v. And then v will be 3 plus 5, it's 8, right? It's 8. So basically you try all the vertices points in the graph. And I need to make it longer. Maybe that it's y minus 4 is here. Should be here. So that is, I think. Okay, and then try again the 1, negative 3, 1, negative 3. Okay, 1 plus 3 is 4, so 4 is here, and 3 minus 3 is 0, so I think it's here. So this one. This point, and then try 3, negative 1, 3, negative 1, 3, negative 1, it's another 4, 3, negative 1, so 9 minus 1 is 8, so this one is here. Okay, and I believe the rest will be this one, right? Check. It should be rectangle. Should be obvious. Okay. Usually the UV when you transform the xy, will transform into rectangular or square. 1 is 1, -3, -1 and 3. -1 and 3. If we take this, yeah, it's another -4, and then -1 plus 3. It's 0, right? Okay, so it's all here. So now we have u is starting from, suppose that we get phi is from 0 to 8 and u is -4 to 4. So then our double integrations we can take, suppose that this is 3v minus 5u. So no matter from du or dv, they are basically the same, and I mean there is no difference when you take the orders, right? So let's say we have the dv du. So du will be -4 and 4, and v is 0 and 8. Okay, and then we solve this. Oh, forget to get the Jacobian, sorry. Jacobian, what is our Jacobian? It's 1/4. So multiply 1/4 here, okay? And then solve this equation. And you will get some number, and that will be your final results. Okay. It seems quite long, but I believe as long as you can get the equations, all the equations that is boundary from the R, and then you can make the boundary for the image. So this is the image from the R, and you can make it clear distance, clear endpoints for the integrations. Should be okay. And sometimes this type of question, like the number 18, 17, 19, and so on, that is the direct question. So it's definitely seeking the Jacobian. But sometimes maybe the question seeking you this kind of questions, like this one here, from 25 to 30, which it doesn't really give a like notions to change, like you have, like you given like this cosine here, like it seems so intimidating, right? We have y minus x, y plus x, we have vertices. So this gives you ideas. Okay? Maybe we could change this y minus x with u or v, and also with y plus x can be u or v, okay? And then use that transformations, check all the vertices, and then write the new equation. Okay. Find the Jacobian value. First, practically the same thing. So every time you have the this kind of question, first thing is we can find the first procedures, perhaps the Jacobian. So we find the transformation for the equations. What kind of equation that you want to transform? What kind of the new variable you want to introduce? Okay, and then check the Jacobian value, and then check the boundary. What kind of boundary that the question has, and then what is the new boundary? It means that we are going to transform based on the transformation of u and v. Okay? So that means that we need to know this is the u and this is the v, and every xy coordinates we need to apply, and then we have the new coordinates. Okay, we have the new coordinates. So check the coordinates, the coordinates, check, and then we have the new coordinates here, right? Okay, I didn't write the coordinates here, but I hope you get this rectangle is from the vertices. Check back to this equation, and then we get 4, -4, and 0 to 8. That is for the double integration endpoint. Okay, so that's step by step. So yeah, it takes time. But I think one more from this side here before I get into the overview for the rest of the topics. Okay. Any idea which one we should start? The cosine or the e or other one? Any requests? Which one? 26. Okay, 26. Okay, now we have the R, the rectangle close by this line, so we can draw the line first. We can draw the line, and then we know the boundary, right? And because we already know the linear equations, so that means we know what kind of transformations we are expecting. Suppose that we have this expression. So what kind of transformation is based on the question? So for example, we have the x plus y. We have x squared minus y squared. What kind of transformation that we could have? Remember that x squared minus y squared, it can be factorized, right? It can be x minus y, x plus y. And I think that's the best and obvious transformations. X minus y and x plus y. We can take it as u and v, right? So that's the idea of the Jacobian. Okay. So I think since there's no space here, let me copy this question and then take a new paper. Okay. Okay. So since x squared minus y squared, we can, so this is 26. We can write as this. And we also have the x plus y, so we let u is, for example, maybe x plus y. And then v is x minus y. Okay, and then we need to know what will be the x in terms of uv and what will be y in terms of uv to get the Jacobian. Because Jacobian, we need to make this transformation from xy to uv. So we need to know the terms in x and y. Okay, so we saw. I think let's solve this first. So for example, we take minus, so u minus v, and this will be 2y. So y is half u minus v, and then we can take this addition, so u plus v will be 2x, or x is half u plus v, right? And we can take the Jacobian. Okay, we can take the Jacobian. So partial x, partial u. So this will be half partial x, partial v. This will be another half. And then for y, partial u is half, partial y, partial v. It's negative. So it should be, if we cross multiply, we have a negative, right? We have a negative, and because this will be a positive value at the end, we only need the value, so it should be half. Okay. Or let me write here. This should be absolute value here. And maybe it's confusing. Maybe I will just leave that for you. Okay, and then we take the image, because we have this, all these terms, right? So it's directly giving you the u and v, right? So for example, u or v is from 0 and then 2, and then u for x plus y is 0 to 3. So you're given the endpoints directly from this linear equation. So we could write that the x plus y becomes u, and then e, and then the x squared minus y squared becomes uv, right? And then we can write this will be Jacobian half, and then let's say dv du, so 0, 2, 0, 3. Okay. Okay, so we can solve this. So dv will be so e, so it will be u over u euv, right, for dv, and then plug in 0 to 2, and then du, right, and cancel, and then we take the du, so this will be e 2u minus 1, right? And this will be 1 over 2. E with power of 2u, we can integrate that, becomes e 2u over 2, right? And minus u. Plug in 0 to 3. So we have 6 e to the 6 over 4, and then minus, this is 3 minus 3 over 2, or maybe confusing, maybe let me write here just to make sure I'm getting correctly, and then minus 1 over 2, right? So e with power of 6 over 4, negative 7 over 2, so negative 7 over 4. Okay. 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 So I think for this type of the questions, we don't really need to draw the boundary, right? Because it's giving you directly from the rectangular shape that is on R. We have the linear equation, which is precisely our transformation of u and v. So we could get this easily, and we can take into this double integral, right? Okay, I hope the integration part is not confusing. Okay. What you need to remember in the multiple integrals, some techniques from calculus 1, especially the substitutions and maybe integration by parts, you should know that very well. And also some techniques for exchange the double angle formulation for the sine and cosine, especially when you have the squared form in inside the integral. I hope also you should be familiar with that. Okay. Okay, now we move to, I think I will take some overview and yeah, some of the, I think I'll take some examples here. Okay, we will start from the beginning. Can we try the first one? Is it a typical exam question? So I hope I can give you some overview and ideas. So this type of question, like iterations, like double integral questions like this, at least one will be your exam. Probably be more. Okay, but at least one. So in this form, you have dx, dy, right? Dx, dy. Can you integrate this directly with x? Maybe you can try. You're right, the correct one. Derive and integrate. Yes. But there are other ways that is cheaper.
question is, can you do it directly? It has forms together. It has a it has like one big equation. Do you have x in both of this? If you are writing it like perhaps there is a plus, that is to integrate that. Yeah, so there's another perspective. So the question is not asking you to integrate directly. It's asking you what is a possible way to integrate this. You see that we have the x and both of this. Suppose that this is x squared, and then we have the e with power of x, right? And then we are asking to integrate x first. But we know that in the double integral, we can change the order. Right? So maybe if we change the order, if we would like to take the dy first, this will be easier to be integrated. Because y only in the e, right? And e with power of xy, we can integrate if that is with respect to y, if that is the first integrations. So to get the order, we need to see these two, okay, these endpoints. So we start to look at the y is start from 0 to 1, and x is from y to 1. Perhaps drawing this area would make sense. Okay, maybe it helps to give you some logics. Okay, so maybe this will be y equals 0 and y is here, 0 is here, right? And then we have y equal x, and x is from y to 1, so maybe it's here, right? So this is the one that we want to take the integrations for the double integrations. Okay, so we would like to see if we change the order. So let's say the x will be the constant. So x from 0 to 1, right? And then y is from 0 to x. Okay. So we have a new double integrations. When we change the order, so this will be 0, 1, 0x, x squared e xy, and this becomes dy dx. And now it's much more makes sense to be computed. So the inside integrations, we are going to integrate the with respect to y. So it means that the x will be just as a constant. So this will be x squared, and then this will be e xy, and this will be 1 over derivative of xy will be x. And let's start from 0 to x, and we still have this dx. And then exchange the x, and then this will be canceling. So we have x, e, x squared, and then we have minus x, right? When we put it 0, it's 1, right? And then dx. Or maybe this will be, or maybe just leave it as it is. Okay. Now next, what should we do now? We can integrate basically these two, right? Easily. Anyway, let's take a break. So this one here, this is just my is my calculation just for this one, okay, just to help to make sure that we have the correct results. And after we substitute back to x, and we have from this one we get here, right? Okay.
I think if you are familiar with the family of exponential, like x e x squared or x squared e, maybe x with power of 3, power of 4, and etc. I think you could directly write the results as this. Right? Because if you derive this, we have x squared becomes 2x, and then this will be cancelled and becomes x, right? And then e is still e over there, right? If we derive. Okay. So we solve and then we get this as our answer. Okay. But the key component to solve this is to get the change of order, okay, in the integrations. So that will be, I think, the key point. Okay. Maybe one question, this one, the surface area. I haven't really take this as in the practice, the surface area. So suppose you have a surface, z, equal x plus y squared, and then it lies on the region which giving you this r. So it is 0 less than x, x is less than y. So that's for x. And then for y is x less than y less than 1. And it is right into one equations. So what you should do first, what is the surface area? How to find the surface area? Partials, right? Partials. So you take the square root and then take 1 plus the partial x squared plus partial y squared. So you get the surface is z. So z is the one that is perhaps here, and then it will be projecting the r, which is this one here. So we know the integrants, the endpoints for this surface area based on this, right? So we could first, perhaps we could find the partials, and I think it's quite simple here. So z is function of x, y. So the partial x, we get this 1. The partial y is 2y. So we could write down the formulations. Suppose the surface area based on r will be the square root of 1 plus 1 plus 2y squared. Okay, or surface area is, let me write the original formula, 1 plus partial x squared plus partial y squared. Should be dA. And then let's say this is dA, and then based on what we have in the r, 0 for x is 0 to y, and then for y is 0 to 1. Okay, so let's say this is 0, 1, and then for x is 0, y. So we have, this will be 2 plus 4y squared, and then dx, dy. So why I choose dx as the first order of the integrations? Because we are having y equations here. If we take this dy first, then maybe we have trouble here.
when we integrate. So I would like to take the x, because when we take the x, we are going to have x as the integration, and then we put y, which then the next step we can use substitution. It will be helpful if we take substitution after this part. If you take dy first, then you need to take this integration, and it, because you need to put this inside, then perhaps it will be much more complicated. And maybe it's doable, but my suggestion is take this to x first. And then the last will be the y. So this will be resulting this is x, zero to y, and then dy. And then let me put here, and then this will be y, 2 plus 4y squared dy. I will take the u substitutions. This is 2, 4, y squared. So du is 8y dy. So dy is 1 over 8y du. So I will exchange that. So I will have 1 over 8. And then square root of u. If you want to take this into u variables, you can and change the endpoint, but I will take this into just y, and then we could integrate. Okay, and then this will be, let's say I will write in another page just to evaluate this square root of u du. This will be 2 over 3, 3 over 2. So 1 over 12. And I will turn back u into y, which is 2 plus 4y squared, square root. So I will take this and write this as 1 over 12. 4y squared plus 2, and then 3 over 2. And then I will directly get this from 0 to 1, right? And then take this 1. So 1 over 12, 6, 3 over 2, and then minus 1 over 12, 2, 3 over 2, and this will be square root 6, 1 over 2 square root of 6 minus 2, right? Okay, this one should be right. So this will be square root of 6. Okay. Right? Okay, I think okay, right? Okay. I hope you get the idea. This is just substitution for this. get the result here, and I change this u back to this, so we have this. Okay. And then plug in the number. I prefer turns back to what we have because the number is easier to follow. If I substitute the whole thing like we did, I think back in calculus 1, if we substitute the whole thing, the 0 and 1 to be substituted by 2 and 6, 2 and 6. But I think it's also okay, 2 and 6 means that we are going to get this directly back, right? Meaning if we take 2 and 6, this will be u. So 2, 6 was square root 6 minus square root of 2. Right? Same. Yeah, maybe easier that way. Yeah. Okay. Okay, we still have time. Okay, let's move on. Okay, before this one, maybe this one first. Okay. This number, okay, the volume. The rest maybe later on. Okay, so I think it's actually pretty simple because all the planes, they are exactly the constant, right? So y equals 0, z equals 0, and z equals 1. So we can take at least first look at the intersections. When y is 0, then we have the x will be in between plus minus 1, right? So we can see that this is, or if you want to draw, I think you can also draw. This is just a parabola in terms of xy. If you want to draw, I think you could draw. Suppose this is z, this is xy. So should be longer that way because that is the parabola is going that way, right? So parabola will be, this one is one maybe here. And then y equals 0,
from here there is a plane, and then plane will be on this is 0 and 1 perhaps. So we have here is, let's say this is the plane, okay, and then we have another plane that is over there, so we have another one like that. I hope you see this one here, this cylinder, okay, parabolic cylinder. So which means that, but I think since they are on the exact plane y equals 0, z equals 0, and z equal 1, and we only, our concern only the cylinder y equal negative minus x squared, so y will be from 0 to 1 minus x squared, okay? So I will take this y as our function of two variables. If you have three triple integrals, I will take this as, so this cylinders will serve as a function of two variables, and then the other two will be a either constant or function of one variable. But since we are not having any other variable or any functions, we have all the constant that we need. For example, z is from 0 to 1, so we can take the z 0 to 1 as our constant, the endpoint. So we could write down the volume. The volume is basically, this is the boundaries, supposed boundaries E, and then this is just dV, okay? This is just the formulations. So what we need is, we take, let's say, the function of two variables for y, so this will be 0 to 1 minus x squared. So this will be dy, okay? And then I will take the z as in the 0 to 1, and x is defined by this. So either dx or dz, you can interchange between those. So x will be from negative 1 to 1, okay? So this will be negative 1, this will be 1. So this will be negative 1, 1. So I will take this as dx and then dz. And then we can take, like for example, because this 2 is basically, or perhaps if we take first, the dy becomes 1 minus x squared. And since this is a constant, so we can use Fubini directly. We can substitute, and perhaps we can directly take this we can take this. So basically I can erase this, right? Because this is just 1. So this will be x minus half x cubed, 3, sorry. So this will be 1 minus 1 over 3 and minus minus 1 minus plus 1 over 3, right? So this will be 2 over 3 minus 2 over 3, so plus, so 4 over 3. Okay. Okay. Okay, any question first? Any question first? I hope you can check the other questions. Check the other questions. Maybe we can get to this this one because we are still learning the Jacobian. Maybe we take the Jacobian, another Jacobian here. Okay. So whenever you have a functions that it's quite complicated and it seems it's giving you some certain boundary, either some equations, linear equation, or vertices, points, it is obvious that it should be, or perhaps it gives you some clue that you can translate or transform the functions or transform the variables. Okay, transform the variables. So I hope you can try this type of questions. I will put this exercise in the Moodle. I mean the whole notes. Check in between. There are some exercise from the textbook, and also I will add some exercise from other sources as well. With some question that we have done before. I think one or two are my example. So if you are given this, and it is pretty obvious, right? Pretty obvious. I think you should see the skin. You see the y minus x and then y plus x. So perhaps you should transform the variable to that. So u and v we can take into that. And we have the points, and put the point into u and v. And you will get the new coordinates for uv, right? Okay? So which means, what I mean is, we can take this perhaps taking u u is y minus x, and then v is y plus x, and then we have all this point, right? So for 0 and 2 we have a new uv, which is 2 minus 0, which is 2, and then y plus x. So 2 plus 0 again, so 2, 2. And then 1, 1 will be 0, and then 2, and then 2, 2 will be 0, and then 4. And then 1, 3, this will be 3 minus 1 is 2, and then this is 2, 4, right? So we have a 0 to 2 for u, and then v is 2 to 4. Okay, so from these new points, and then we can set up the Jacobian. How to set up? We need to make this simplified in terms of x and y. So we are taking this, let's say, minus. This is u minus v. This will be minus 2x, or x is half v minus u, right? And do the same thing. We have u plus v equal to y. So y is half u plus v. And then take the Jacobian. So this will be negative 1 over 2, and then this is half, this is half, this is half, and the same component, this should be half. Should be negative half, but it will be absolute value, so I will just write the value itself. Okay. And then we take this u over v from here. So this is u, this is v, and I will take perhaps this is half the Jacobian, and then let's say we have dv du, 2, 4. Actually, it can be du dv or dv du. It's up to you. But I think I will take dv first so that I will pull out the ln out of it. And since this is the Fubini, we can exchange. So half, we can write this. Okay, we can do this, right? We can separate this because they are, the endpoints are constants, and we can separate the functions as well. Okay. This will be 2. I will cancel this, so this will be cancel out this and that. So this everything will be just 1. So we have here is ln v from 2 to 4. So ln 4 minus ln 2 or ln 2. This means we can okay. Okay, so far so good. Oh, I have another one, more interesting. Okay, maybe last part. Okay, last part. So Jacobian, volume, the double integral surface area. And I think some of the question that we have, I think I skipped one question, is about polar. So double integrations, when you can change the curve, the function into polar, maybe it will be easier. You can change and then solve the polar integration. Okay, now move to this. Okay, either the first, maybe take the first one. Okay, the first one, sketch the region and then change the order and evaluate. It has instructions. Okay? It has instruction to change the order. So that means it could help out for the solutions as well. So let's start this. Okay? And if we have time, maybe start the number 5 as well. Number 5 here, maybe just a quick review. This will relate to. So this is the surface. Okay. This is the area. Remember that when we have this supposed triple integral, this E will be our figure, right? This E, no matter what the function is, because we cannot really see what kind of functions. Okay? If you have seen the movie, what's it called? Interstellar. It's called like tesseract, blah blah blah. That is the 4th dimension, which is basically they are trapped between time and space. So the person can be anywhere, but the world, the 3-dimensional world cannot see the 4 dimensions. Okay, but yeah, that's a little bit more fiction than science, but it's interesting. So this part will be our function of 2 variables. So suppose that the z will be our inside of here, the inside integrals. The outside, we suspect it should be the area. Okay, we suspect to be area. And since this is the circle, then we might have a polar. We can change the polar for the double integrations. For these two. Okay. So first we can integrate with respect to z for this one, and then solve. And then after we get the z, we then evaluate the dA, which the dA will be this polar. Okay. Maybe I explain this one first. Okay, maybe because I haven't covered the polar, right? So if we look at the region, suppose that D is the region. So this is, suppose that this is D. So this is the D. Okay. So let's say this is D. So D is x squared plus y squared equal 4. So we have, first is R is from 0 to 2. And then what will be the theta is from 0 to pi over 2, right? Okay. So at least we know the D. Okay, now our Z is start from, because it doesn't give you anything except that it is going to be the first octant, meaning that all the quadrants will be positive. Okay. So let's assume that Z will be starting from this 0. So let's say the Z is from 0 to this plane. Z equal 3 squared of x squared plus y squared. And let's write that. So this is, let's say this is D, the double integrations for the area. And for the Z, I will write here from 0 to 3 squared of x squared plus y squared. And we have x, and then this will be dz, and then dA. Okay. We suspect that d and dA, because we have the polar, later we can convert, okay, later. But we compute this one first, the dz. We compute dz, then we have d, then this will be z. So this will be 3x, and then square root of x squared plus y squared, and then dA. Okay, now we can convert to polar. Convert to polar, theta, and then r, and then this will be r squared, right? And then this will be r, and then the x will be r cosine theta. Okay, so we can write 3r, and then, or r squared, because we multiply, so r squared cosine theta, and then multiply with r dr d theta. Okay, so we can, let me write again here, 3r cubed cosine theta dr d theta. And basically we can separate this two, and then the r will be 3r cubed, and then the cosine theta will be sine from 0 to pi over 2. This will be 1 over 4 from 0 to 2. This will be 1. Oh, this is not 1, sorry. 3, because it's 3, right? Okay, so 16 divided by 4 is 4, so 12. So 12 minus 0, 12, so this will be 12. Okay. And since now it's already almost 3, and I need to take some feedback, one more time feedback, okay, before the final. So the rest of the questions, I will leave that to you. I hope within this week I can give you like some notes for the rest of the questions. Also, maybe the answer key for the last question that I put in the model. Right? I think last year, final exam. Remember the final exam for last year? There is no triple integrals. But for this year, maybe there will be. There will be, okay. But I will make it balanced so that it should be. So you should be able to make it. I'm trying my best to get the balance. So there will be like maybe the questions like heavy, but there is some question that you should be able to do it. Okay.